Okay, Resnet. I'll try to implement Resnet from scratch today. So why? Because first everybody just says implementing something from scratch just helps understanding it. This is the first reason. And Resnet is great, well-written paper. Also, most importantly, I'm just reading this book, Deep Learning for Coders with AI and Pytorch. And the 14th chapter of this book is about Resnet, how it works, why it's important, this kind of stuff. Also, I was following book reading sessions from Weight and Bias's YouTube channel. So there's lots of information. I hope I have well prepared implementing Resnet from scratch. Okay, let's start. So in this notebook, you will see there are two diagrams at the top of the page showing some training and test errors of two different architectures, and 20 layer one performs better for the training stage and also the test stage. So why? Because there's a problem with the training. Also, as you can see, the test result is not so good. So that means adding extra layers at the end of an architecture, a network, don't help it to perform better. Okay. In 2015, Resnet architecture just solved this problem. This is why it is too important. One of the reasons. So let's assume we have a 56-layer network. And think about it. The first 20 layer is already trained, and the next 36 layer just doing nothing. And theoretically, this network should should perform at least as good as 20 layer architecture, right? Because this 36 layer don't do anything. So where's the problem then? The problem is the insight is learning doing nothing is not so easy. So for example, in multiplication, it's easy, right? Just multiply 1 and 20, it's 20. Nothing changes. But in terms of convolutional layers, it's not so easy. So that means if we find a way to train the second part of the architecture a little bit differently, maybe a little bit better, then maybe we can end up with a better network. So this paper is about this kind of, let's say, solution. And this is how Resnet architecture implemented in the actual paper. It's a bit different how I explained, but the idea is pretty similar. So in this architecture, we have basic blocks. They call it basic blocks instead of stack of layers. These basic blocks consist of convolutional layers again, no problem at all here. And also a skip connection. 2 convolutional layers and skip connection. So we have 1, 2, 3, 4 basic blocks here. This is stem. This is a part of the 34-layer residual network, not all of them. So, but what is so important about this basic blocks and how basic blocks solve that problem? Let's see what's going on here. So let's assume we have a activation from the previous layer or basic block X. So, and we feed this a portion of network with X, but plus we have a shortcut here to here. That means first we feed the X, we feed the network with X, and at the end of the basic block we just add X plus this calculation, X plus Fx. So what is the effect? The effect is, if you have any familiarity with the L2 regularization, or let's say weight decay, if you, let's say, if you add these two X and Fx together and back propagate from this way, these weights just tend to be smaller and smaller. This is how L2 regularization works. So if you need any explanation why it happens, please check Andrew NG's Resnet, let's say, video. I will put it into this notebook. But it just works like that. That means these two layers in the middle just learn to be a identity layer. They don't, their, let's say, effect on the, let's say, total total activation here is getting smaller and smaller, such that we feed this with X and we get X from here. Fx just tends to disappear. Okay. At the same time, we still need these layers for calculation. They're still trainable. We just want them less and less effective on the total result of this activation. This is the point. We want them very close to be a identity layer, but not exactly. So let's see what's inside the Resnet architecture. So as you can see here, we have a convolution layer, normal layer, not a basic block, some basic blocks, an average pool layer. At the end of the architecture, the network, a fully connected layer for 1000 classes. Okay, for first stage, we need 3 basic blocks. For second, 4. For third one, 6. And the fourth one, 3. Let's check first the Resnet's Pytorch Resnet implementation, then implement our version from scratch. Okay, I tried to create a Resnet from Torch Vision library, a model library. First, okay, I think it's a very good place to start. Import Torch here and import torch.nn as nn. Okay, and import torch vision dot models as models. So in models, okay, in models we have lots of different architectures already there. Resnet, 34. That call it and check what's inside. Okay. Resnet here. First our convolutional layer like this, and batch normalization, ReLU, max pool, and basic block starts from here. 1, 2, 3 for first stage. 3 basic blocks. For the second, again 4 basic blocks. 6 and 3 average pool and fully connected. As you can see here, average pool and fully connected layer. Let's start with basic block. We need a class basic block. Okay, what we need here is nn.module, and we need to initialize it with dunder init. Oops. With in channels out channels. Also stride 1. Do we need this? Okay. And start with conv 1 as here. So equal conv and n dot conv 2D. Okay, with in channels and out channels. Okay, plus kernel size 3. Do we need padding? Padding, yes, we need padding because we need the image size same. Otherwise, it's not easy to implement this network. Padding equal 1. Okay, and a batch norm self dot enter self b and 1 equal nn batch normalization batch norm 2D without channels, because it's already the channel size is changed. Out channels. Okay, good. And copy this. Okay, copy. Okay, and paste. Okay, conv 2D. This is not out channels, in channels, but out channels. In out, and out. Okay, and this is out. And in between, we need self dot activation. What is it? It equal to ReLU. Doesn't matter. ReLU equal nn dot ReLU. Okay. Okay. So, do we need something else? Not now, but we will, let's say, define a forward function. Forward. Okay. Self x to self. Anyway, just put it there. Okay. Yes. First, we need to create skip connection. Let's say skip connection equal x, because we want x just go this way. Okay, skip connection first. Okay, x, then x equal conv 1 x. Okay, conv 2x, sorry, self okay, dot and in between x equal bn1 x. Okay, bn2 x, and in between x equal x. Okay, no, value x. Okay, I think we're okay, right? Skip connection. Okay, skip connection as x, and x plus equal skip connection, and return x. Okay, let's see what happens. Okay, so let's create tensor, a random tensor called x torch dot random. Okay, one tensor with, let's start with easy one, 64 channels and 128 by 128 let's say image. Okay, I don't want to change anything at all because in channel and out channel is same. I expect a 64 channel output from this basic block. Create a basic block, block equal basic block 64 by 64, right? Okay, oops, answer int random, let's see, int, where is it? In channels, groups, what's going on? Okay, basic block and int, where is it? Okay. In channels, all channels, kernel size, one in channel. Okay. In itself, maybe. Okay. Cannot assign module before module. Okay. Okay, there's a problem here. Super dot init. Oops. Init. Okay. Okay. Okay, good. Good. Let's see what happens if we feed this basic block network with X. bn1 is not defined. Okay, of course, self dot okay. Has that bn2 is here. Okay. Here, let's see the shape. Okay, I just feed with 64 channels and get 64 channels. Image size is still same, no problem at all. But if the channel sizes are different, like between basic blocks, sorry, between stages. For example, layer 1, 64, 64, 64, 64, but here 64 to 128. Okay, we need to solve this. How we convert a 64 channel image tensor to 128 channels tensor. Okay, we need to downsample it. How we can downsample it? For example, if, let's try this way, if in channels equal out channels, then down self dot downsample equal none. Do nothing. Okay, like as it always was. But else, then self dot downsample equals here convolutional and batch norm layer. So 64 to 128. That means I need a sequential module here. Let's see. And then dot sequential. Okay. As a first layer, I need to have nn dot nn dot compute in channels all channels in channels all channels, but at this time kernel size equal 1, because I want model to use 1 by 1 kernel for each two cell. Okay, because I want to downsize it. Okay, how I can do this? So let's see. Okay, count 2D in channels, out channels, kernel size equal 1. And n dot batch norm 2D out channel. Okay. Okay. Now, what should I do here? Okay. X equal x plus skip connection. Before this addition, I need to check if self dot downsample is defined. If it was, then skip connection equal self dot downsample dot x, not dot x, dot skip connection. Okay, so if it was 64 channels here, if I downsample it, it become 128 channels. Okay, then I add this one, x will be, okay, 128 here, and this will be also 128, and I guess I get a right answer. Let's try this way. Let's try this way first. Okay, it's 64 to 64. I give it 64. I take a 64 channel image, no problem at all. But if I change this 128, what will happen? Let's check it. Okay, 100. It's right. Okay, 100, and it's in channel is 64 and out channel is 128. It's okay, but there's a problem. The image size still 128, which is not right, because we expect this image size to decrease in every block, right? Then what is wrong here is kernel size 1, but stride is not 1 but 2. Stride equal 2. If there's a downsample, then we need to change the image and decrease the image size by 2. Okay. Oh, what's going on? Okay, stride is nn.module, and we need to initialize it with dunder init. Oops. With